Hello students, in this session we will do the chapter of some basic concepts of chemistry. This will be the foundation chapter. So the concepts that we will see in this chapter you might have learned already in your lower grades, fine. So majority of the concepts will be like the basic understanding that you might have already known. Got it? So we need around like 2 sessions to complete this chapter. By the way, in this session we will do like 4 to 5 different laws. That will be like law of conservation of mass, basic easy one, and then definite multiple proportions. Finally you will see like Avagadro law. Okay, so we will do around like 5 different laws. All those laws will be the basic things. Fine. So from your 10th grade itself, you might have learned already all those laws that I'm going to tell you. Anyway, that will be the foundation that we need to know before building up all the rest of the chapters in this chemistry. Okay, got it? And finally we will see like what is meant by Dalton's atomic law and Dalton's atomic theory, and then we will do the atomic mass unit. Fine. So what will be the unit that we need to know to learn to find the mass of one particular atom of something of that sort. Okay, so that will be a very microscopic unit. Okay, so that will be equal to certain number, and we will find a way to choose that particular number, right? So these are the concepts that we will see in this session, right? So this will be the shorter session. We will need around like 40 to 45 minutes. That's it. We'll complete all the concept. Okay, so every concept will be like an single statement based concept. Okay, so this will not be an intertwined concept like the concept that we see in physics. Okay, so everything will be straight away and it will be easy. Got it? Finally, we will see the atomic mass unit, which is something a kind of a microscopic measurement of mass, and then that number will be equal to some microscopic quantity, and then we will define a way to match that particular number by doing the experiment. Okay, so what sort of experiment that I actually have to do? So a basic understanding that too will be dealt. Got it? So these will be the steps that we will see in this session. Fine. So in the next session we will do around the rest all other chapter that will be like mole fraction, mole fraction, molality, molarity, things of that sort, right? So those things will be done in the next session. Got it? Fine. So let's jump into the concept. So here you have got like the first basic understanding, which is like the molecule and then the compound. Fine. So how should I actually differentiate between a molecule and then the compound? Fine. So we obviously know atom is a single entity of an element. When two elements combine, when two atoms combine, they just produce molecule or compound. Fine. So if it has to be a molecule, then it has to be a similar atom that has to combine. In the case of compound, you need to have like two different atoms and they are going to combine together, and then it forms a compound, right? So with the case of molecule, two atom has to be similar. In the case of compound, dissimilar atoms could combine to form compound, right? So that's the differentiation between the molecule and then the compound. So the example for the molecule will be like oxygen. So here OO, both the atoms are oxygen, it combined and it produced O2. Same way you could put like H2, N2, whatever it is, like the example goes on. And then you have got like compound. In compound you need to have at least one different atom. If that was the case, then example could be like CO2, right? So you have got like two same atom, which is like oxygen, it got combined with one of the different atom that was carbon. So together it gave you like carbon dioxide. Then we could keep on going with n number of compounds. Then let me take one more example into it, which will be like ammonia. That will have one nitrogen and then you will have like three hydrogen into it. Fine. So you should be clear with the differentiation between the molecule and then the compound. That has to be clear. Then you have got something called accuracy, precision, and all those things, right? So accuracy, precision, we have already learned clearly in the physics itself. You should be clear with that idea. So I'll just give you an overall understanding of the difference between accurate, precise, and all those stuff, right? So we are just going to do an experiment, and the result of the experiment was like 1.54 centimeter. I measured a length and the length was equal to 1.54 centimeter. So that's the exact value. Got it? So someone has measured it and kept to himself. Then the other guy is going to measure it and I'm just going to compare. Is it accurate or is it precise or is it both accurate and then the precise, right? So we know the true value, which was equal to 1.54 centimeter. Then you have got, then they're asking us like accurate but not precise. Got it? Which means the value that he has found was accurate, which means it was equal to 1.5, something of that sort, but he didn't resolve it to a maximum extent to find the next decimal place, which was like 4 centimeter into it. He just found like only one decimal places, which was 1.5. So when compared to the true value, it was accurate because it matched with my true value, but it wasn't precise because he could have found like 1 or 2 extra decimal places into it, right? So this answer is accurate but not precise. So the first one should be clear. Then you have got precise but not accurate. So here in this condition, he has found like extra decimal places, but the answer was wrong. If that was case, then it is like precise but not accurate. So he has found something like this 1.456 centimeters, something of that sort, whatever the number it could be. You should get the notion and idea that I'm telling you. The actual answer was like 1.54. He didn't even find the first decimal place correct, but he resolved it to like two more extra decimal places into it. If that was the case, then obviously he has a good instrument to measure it, but the problem is he measured it not accurately. Okay, so here it is like precise but it is not accurate, so it should be clear. Then you have got the next one, which is like accurate and then the precise, which means he has measured the true value correctly up to the same decimal point. Still he measured extra more decimal places into it, which means he resolved it to much more greater extent to get the accurate and then the precise value. If that was the case, the answer could be something of this sort, which is like 1.54. So he measured 2 decimal places correctly to that of the true value. Same way, he had a good instrument, therefore he was able to measure still more extra precise. Got it? So this answer is both accurate and then it is also precise. For example, 1.547 or 6, whatever it is, 1.546 centimeter, right? So you should be clear with the idea that I'm telling you. Okay, you shouldn't have any doubt at this part. Got it? So we should be clear with the word accurate, precise, fine. So you will not get questioned something related to accurate and precise. Okay. The reason why I'm teaching you this one is you need to have like clear understanding of the terms, right? You should know what is meant by accurate, what the term actually represents. Same way, you should know the difference between the accurate and then the precise. These two are not the same thing in physics and chemistry while doing numbers. Got it? Fine. So you should be clear with this stuff. Then we will see the 5 laws that I've told you. The first one is simple, straight away one, which is like law of conservation of mass. So here the example that I've taken is I've got a carbon solid, whatever it is, coal, coke, whatever it is. I've taken solid mass of carbon and then I'm going to burn it. Like, right, once I ignite it, what will happen? Carbon will burn in the presence of oxygen. We know that stuff. Therefore, when these two things combine, it will end up producing the carbon dioxide, right? So the final product over here is also in gaseous state, which will give you like carbon dioxide. Got it? So this one is also in the gaseous state. Got it? So carbon was in solid form, same way oxygen was in gaseous state. These two stuff combined and then it produced carbon dioxide, which was in the gaseous state. Fine, right? If this was the case, whatever the reactant that was there, whatever the mass that got consumed, the product should also have the same amount of mass, because in this situation it is pretty obvious there wasn't any destruction of mass. What it one compound combined with the other compound and then it produced a new compound into it, right? Therefore, there wasn't any mass loss in this situation, which means whenever you have a chemical reaction into it, there wouldn't be any loss in the mass, right? So only when you have like nuclear reaction, when the protons or neutrons are going to interact, in that situation we will have the mass defect, which means the decrement in the mass. But in this situation you will not have any decrease in the mass. Therefore, the mass of the reactant has to be same as that of the mass of the product, which is the first law, which is called as law of conservation of mass. It should be clear. The statement will be like total mass of reactant, got it, and total mass of reactant and product will be same. You need to have same amount of reactant and then the product, right? So this one is law of conservation of mass. It should be clear. No doubt should be there. Then we have got law of definite proportion. So law of definite proportion. The name itself clearly suggests, which means something has to be constant. Whatever the reaction that you do, if you get the same product, then the composition will be same. It doesn't depend on the nature of the reaction that I've chosen. Got it? So here, let me produce carbon dioxide using like three different cases. In the first case, this is like a simple one. Here you have got a chunk of wood. So I have taken a wood and then I'm going to burn it. So we know wood contains carbon, hydrogen, oxygen. Okay, so it will have a combination of glucose and cellulose and all those other stuff in that wooden material. When we are about to burn, it will give us carbon dioxide, water, and all those other stuff, right? Whatever minerals it will have, it will just all those things will get combusted and then it will get into a vapor state, right? Here in this case, majority of the byproduct will be carbon dioxide and then the water. I'm just going to only consider the carbon dioxide, right? I've taken wood and then I'm gonna burn it. When I burn it, it will produce carbon dioxide. What I'm going to do is I'm just going to trap that carbon dioxide. Fine. So that was the first experiment that I did over here. Here in this case, I just burnt it. It produced carbon dioxide. Got it? So it produced carbon dioxide. Fine. So this was the first experiment. The second method in which we are going to produce carbon dioxide is by breathing. Fine. So here there is a guy who is breathing, which means he is intaking oxygen. Fine. So we have like nitrogen, oxygen, and all those other compounds in the atmospheric air. When we inhale, 20 to 25% of that gas will be like oxygen. So this oxygen will get diffused into the blood, right? So this oxygen will be used to combust the food that we intake, right? So all those chemical reaction will take place over there. Fine. So we will have diffusion of nutrients into the bloodstream and all those things will happen. Again, this bloodstream will carry back the oxygen, right? So after the combustion, same combustion, a kind of combustion will take place in our stomach. Okay, so you will have the chemical reaction into it, and then finally the intake will be oxygen through breathing to breathing in air. Same way, when we breathe out, we will exhale carbon dioxide, right? So here also the byproduct, the end product was like carbon dioxide. I'm just going to trap this carbon dioxide that I exhale. Got it? So this is a pattern by which I can produce carbon dioxide, right? So next, let me take any fuels. It could be like petrol, diesel, kerosene, whatever it is. I'm just gonna burn it, right? I'm just going to ignite it. If I ignite it, generally in the with the case of kerosene and then the petrol, you will have like carbon hydrogen mixed composition, right? So when it burns, it will also produce carbon dioxide and then the water, right? So when I burn it, it will end up it will end up releasing carbon dioxide. Fine. So in this three different cases, the experiment was different, but I just got only the carbon dioxide as a byproduct. Got it? So if this was the case, whatever the experiment that you do, if it is going to produce carbon dioxide, this carbon dioxide will have the same proportion. Fine. So it will have like one part of carbon, same way it will have like two part of oxygen. If it was like different experiment, it's not going to have some other composition. So the composition will be same irrespective of the experiment that I do, right? So that's what is meant by law of definite proportion. So here I have got given compound contains same proportion of element by weight. So the ratios will be same. If it was like one proportion of carbon, that's going to be one proportion of carbon, which will combine with two proportion of oxygen, right? So that's what this statement represents. You have got given compound, which means the same compound contains same proportion of element. Okay. So it will have like same proportion of element. When you measure it, how do we actually measure it as? We will measure it in weights, right? So by weight. Got it? So this is what is meant by law of definite proportion. It should be clear. Then we have got law of multiple proportion. Next law is law of multiple proportion. Here I'll just take the same reactant, but the product will be different. Got it? If that was the case, then in which format I actually have to consider the reactant. That's what I'm going to get it over here. Here you have got the simple experiment, simple reaction, which is like hydrogen that's going to combine with oxygen. and in the first situation it is going to produce water. Okay, so in the first case obviously it's going to produce like water. Okay, got it. So that's the first reaction. In the second reaction, same way, I'm just going to put in extra more oxygen into it. Okay, so I'm just going to pump more oxygen in the case of the second reaction. If that's going to be the consideration, then it forms like hydrogen peroxide, which will be like H2 or 2, right? So we'll learn more in detail about this hydrogen peroxide and all these reaction in upcoming chapter. As if now what you need to know is, like, you have got the same reactant, but in the second case I just gave like more amount of oxygen to it and then it formed hydrogen peroxide, right? So here in this situation, multiple proportion actually means when you have fixed mass of one element. Okay, so this hydrogen, I'm just going to have a fixed mass, right? I'll have to fix any one of those two masses. So here I'll just fix the hydrogen mass, which is like I just took like 2 grams of hydrogen. Got it? So do not worry about this numbers that I'm going to take. Anyway, as we learn like mole and all those concepts, you'll get to know why did I take like 2 grams in the situation. But whatever the case it is, initially I just took like 2 grams of hydrogen in both those situations. Fine. I just need to produce like water in the first situation, and in the second situation I just need to produce like H2O2. If that was the case, then in what pattern should I actually take this oxygen? That's what I need to get over here, right? So in the first situation, when I took like 16 grams of oxygen, it just got completely reacted and it produced like 18 gram of water. Okay, so the answer for the first reaction will be like 18 gram. Fine, so this is how the reaction is going to be. Here I've got like 2 gram of hydrogen that's going to combine with 16 gram of oxygen and it got completely reacted and finally it produced 18 gram of water. In the case of the second reaction, you have got like 2 grams, so that's the fixed mass that will combine with 32 grams of oxygen. Got it? So do not worry about this number. It's just take it. I'm just giving you straight away. So here I've got like 2 grams of hydrogen. Same way when I do the experiment, it was like 32 grams of oxygen that was needed. So these two stuff got combined and it produced obviously the addition of those two stuff because there wouldn't be any decrement in the mass. Therefore, it produced 34 grams of H2O2. This is the understanding that you need to know. So here, when you look at this mass, when you look at this element, it is obvious element or compound, whatever it is. When you look at this molecule, it is pretty obvious. It is combining with the fixed mass in some whole number ratios. Okay, it is not like 1 is to 1.5 or 1.7 in that pattern. It is clear. 16 into 2 will give you like 32 gram, right? So law of multiple proportion actually means when you have like one mass to be fixed, which means one of the reactant to be like constant, when mass of one element is when mass of one element combines with the fixed mass of other element, which is this hydrogen, when these two stuff combine, the ratio of the masses, so this mass which is not fixed will be in what ratio? Will be in the ratio of simple whole number. Okay, so this one, then the ratio of the masses that got combined with the fixed mass will be in the ratio of simple whole number that will not have any decimal places into it, which is something like this 1 is to 1.5 or 1.7. It will not be in that ratio, it will be in the simple whole number ratio. So that is what is meant by law of multiple proportion. It should be clear. So here the only term that I need to fill is simple whole number. The ratios will be in simple whole number. Got it? It will not have any decimal places, right? So that's the law of multiple proportion. Then you have got like Gay-Lussac's law, which is with respect to the gas and with respect to the volume of the gas. Got it? So here I've got Gay-Lussac's law. Here what I'm going to take is, you have got like hydrogen and then oxygen. Same way it is going to produce like water. Fine. So here I do not consider the masses. So what, by comparing mass, I have just already done law of multiple proportion. Here I'll have to consider the volume, which means this is in the gaseous state. Okay. If that was the case, then it has to combine same way with simple ratio. Okay, so here in the first situation I took like 50 ml of hydrogen. Got it? Let me put it this way. So that will be easy. So in the first case, I'll just take like 100 ml of hydrogen. The reason why I took it 100 is because here, if I do solve this, if I do balance this equation with stoichiometry, you'll have like 2H2, right? If I have to balance it, that will be like 2H2, and then that will give you like 2H2O. Same way, if I take like 100 ml of hydrogen, I just need 50 ml of oxygen. When you do experiment in terms of volume, this is not in terms of the mass, this is in terms of the volume that is about to occupy in the given chamber, right? So I'll have to take like 100 ml of gaseous state hydrogen, and then if I combine it with 50 ml of oxygen. If it was like 50, then here it should be like 25. So to make it fancier, I'm just taking it in this fashion. So it will combine with 50 ml of oxygen, and then it will produce 100 ml of water in gaseous state, which means like water vapor. So it will produce 100 ml of water, right? So this is based on the volume consideration. Got it? So here I am just considering the volume. So this is based on volume consideration, right? So it should be clear. The statement for Gay-Lussac's law will be when gases combine in a chemical reaction, they do so in simple ratio. Okay, so they do so in simple ratio by volume. Fine. So same way, this one will also be in whole number, which means like if it was like 50, then it will be like double the amount or triple the amount. So that is how the gas will combine to proceed the reaction. Got it? When gases combine in a chemical reaction, they do so in simple ratio by volume. Simple ratio. Here, with the case of Gay-Lussac's law, I'm just going to consider the volume. Therefore, it will be like simple ratio by volume. And by the way, this is a gaseous reaction, right? You shouldn't have any liquid state or solid state reactant into it. They do so in simple ratio by volume. Got it? So that's like one more consideration into it, which is this hydrogen and this oxygen has to have same temperature and pressure. Fine. So you shouldn't consider take the hydrogen with the temperature of 100 degree Celsius, and then oxygen shouldn't be in the temperature of 50 degrees Celsius. These two stuff has to be in the same temperature. That is when for the volume that I'm going to consider, you have like same number of molecules into it, right? Therefore, one of the important consideration over here is these two, hydrogen and oxygen, should have same temperature and then the same pressure, right? Whatever temperature and pressure, that is not a mandatory parameter over here. The point is you need to have same temperature and pressure. It could be whatever temperature or whatever pressure, that doesn't matter over here, right? So this is what is meant by Gay-Lussac's law. So Gay-Lussac's law represents when you have like two different reactant that will combine with the same simple ratio by volume in the combination, right? So that you should be clear with this Gay-Lussac's law. Then we will see what is meant by Avogadro's law, right? Avogadro's law is a kind of continuation of Gay-Lussac's law that we have already seen. So here I'll just do the same experiment one more time, which means I'll take two parts of hydrogen and then one part of oxygen. It will produce like two parts of water vapor. Okay, so if that was the case, here in the first situation, let me take the hydrogen over here, which means I know hydrogen is actually a diatomic molecule. Therefore, you will have two hydrogen combined. Same way, let me take two molecules, only two. Okay, so two molecules of hydrogen atom, and then I know I just need to have double the amount to combine it with the oxygen, right? If that was the case, same way I'll take one more set of two molecules of hydrogen. Got it? I'm just going to combine it with one set of oxygen. Fine. So you'll have oxygen. Same way you have like two oxygen molecules into it. If this is going to combine, what will it actually produce? It will produce like water vapor, right? So in the case of water vapor, I know water is actually a compound. It will have like two hydrogen into it and one oxygen. So obviously here you have got like 4 oxygen atoms, here you have got like 8 hydrogen atoms. When it is about to combine, it will produce like water molecules, right? So this is going to produce water molecule, which will be, which will have 2 hydrogen and 1 oxygen into it. Same way it will have like 2 hydrogen and 1 oxygen into it, and then it will have 2 hydrogen, 1 oxygen, hydrogen, 1 oxygen. Got it? So this will be the product that is formed over here. So when you consider this reaction, the mass doesn't come into picture, because when you consider one molecule, only one molecule of hydrogen, and then it is in gaseous state. Okay, so the surrounding space is empty. Got it? So majority of the space in this situation is empty when compared to that one molecule. Let me give you an consideration. You just consider a football, and the rest all other ground is a kind of empty one. So that one football is actually the hydrogen molecule. You can consider the complete stadium to be the empty space. So if that's going to be the case, then it should be pretty obvious majority of the space around in the gaseous state is going to be empty, right? So here equal volume of the gas. So from this I'll get the Avogadro law, which means it doesn't depend on the nature of the gas. If I know oxygen is more heavier when compared to the hydrogen, but in this situation the space is more empty, that it is like freely arranged in that gaseous state. So if that was the case, we do not want to worry about the mass of the element or the nature of that particular element. Okay, so that thing need not be considered, because majority of the space in the gaseous state will be empty, right? So equal volume of all gases at the same temperature and pressure, right? So if you're going to compress it to a maximum extent, that's a completely different kind of situation. So this gaseous molecule will just get compressed to liquid state. That shouldn't be the case. When it is in the gaseous state, generally when it is in a gaseous state, surrounding empty space is going to be much greater when compared to the tiny molecule. Therefore I do not want to worry about the nature of the molecule, whether it is like oxygen or hydrogen or carbon dioxide. It doesn't matter. Whatever the molecule that you choose, if it is in the gaseous state, then if you consider the same volume of gas, then it will have like same number of atoms into it. It doesn't matter whatever the molecule it could be, the number of count of that particular molecule will be just the same one, right? So here equal volume of all gases at the same temperature and pressure, whatever the gas it is, it should contain same equal number of molecules. Okay, same number of molecules or equal number of molecules, whatever it is. So it should contain equal number of molecules. Got it? Here I didn't consider the mass. Here I just considered the volume, the space that it occupied. Fine. So here it is in gaseous state, therefore it is very much spaciously arranged. And then you have got like two parts of hydrogen that will combine with one part of oxygen, and then it will produce like two volumes of water. Got it? So you should get this notion why like three parts of reactant produce like two parts of product, because this gaseous state is actually freely arranged. Therefore you have like more empty spaces into it. You do not want to worry about that tiny extra masses. Okay, you do not want to worry about that tiny particle which is going to have extra mass into it. You do not want to worry about that one, because the majority of the space, 99.9% of the space is actually empty, right? So that's the understanding and thinking that you need to know, right? You should be clear with this Avogadro law. So Avogadro law will work out when the reactant and the product are in the gaseous state, right? So that is when it will work out. If it is in solid or liquid state, that's a completely different story, because in solid and liquid state it is much more compactly arranged when compared to the gaseous state. Okay, so when it is in the gaseous state, obviously it is randomly moving in different directions, right? Got it? So you should be clear with this idea of Avogadro's law. Then we will see like Dalton atomic theory. So this is a kind of basic thing that we already know. So the guy who, or the scientist who postulated this theory, have given us like 5 different statements. That is, let me read all those 5 statements into it. Matter consists of indivisible atom. Okay, so this is the primitive first stage understanding. So when you have an object, whatever it is, when you look at an object, it will have atoms into it. Those atoms are indivisible, but we know we'll be able to split the atom, and we'll be able to get the protons and neutrons into it. But this is a kind of premature idea, right? So initially, when the people looked into an object, they were able to devise these five postulates, so that this will be the foundation for the chemistry, right? So the first postulate that he gave was matter consists of indivisible atom. Okay. Then you have got all the atoms of a given element have identical properties, including the identical mass. Atoms of different element differ in mass, which means if I take like hydrogen, it doesn't matter. Wherever I just take hydrogen, it will have the same property and same way it will have the same mass, that atom. Same way, atoms of different element. If it was a different element, carbon, it will have like different mass into it. So hydrogen will have different mass when it is in atomic state. Same way, carbon, nitrogen, other element will have its own masses. That will not be related to the mass of the hydrogen or other element, right? So that's what they have given over here, simple one. Then you have got compounds are formed when atoms of different element combine in fixed ratio. We have already discussed what is meant by compound, so that is pretty obvious. When different elements combine together in a fixed ratio, we will end up getting the compounds, right? Chemical reaction involves reorganization of atoms. So when you have a chemical reaction that's going to happen, then there will be a rearrangement of atoms. Whatever atom that you have over the reactant, you will have the same element on the product, but the point is it will get rearranged. The that's what it is given over here. Chemical reaction involves reorganization of atoms. These are neither created nor destroyed in chemical reaction, which means when you have chemical reaction that's going to take place, the atoms will not be destroyed. Only when you have nuclear reaction, the atoms will produce like different elements into it. But in the case of chemical reaction, only you will have like reorganization of those atoms, right? So these are the 4 points that Dalton gave, which is called as Dalton's atomic theory, right? You do not want to know much into it. It's again a overall understanding that I'm telling you, right? It should be clear. Next one will be the last part for the session, which will be atomic mass unit. In atomic mass, I'll fix a very small quantity that will help us measuring the value of the atoms and all those other stuff, right? So this is a very small quantity when compared to the real time units that we consider, 1 gram, 1 kg. That's a very humongous amount when compared to this small quantity, which will help us easily get an idea of the mass of one atom or one hydrogen atom molecule, whatever it is, right? So whenever you measure such a small quantity, I'll use this unit, which is called as one atomic mass unit, right? So to get the value for this particular term, which is like one atomic mass unit, what will I do is I'll just take carbon atom, right? So the carbon atom that I'm going to choose is like C12. So here C12 actually represents that you have got like 12 nucleons into it, which is a combination of protons and then the neutrons. So you'll have like 12 protons and neutrons into it. So obviously in the case of carbon, we will have like 6 protons. Got it, right? You should know this one from the lower grades. So here to get the value of one atomic mass unit, what I did is I just took one atom of C12. So here you have got like 12 nucleons into it, that is a combination of protons and then neutrons. Then what I'm going to do is I'm just going to divide it by 12 because you have got like 12 set of nucleons into it, right? So here next what will I do is I'll just divide it by 12, right? So that's an experiment which is called as Bainbridge mass spectrometer. Okay, you do not want to know about that experiment. The point is when you do that experiment, I'll be able to get the mass of one atom, right? So that's a kind of magnetic field involving stuff. Anyway, the point is by doing some experiment, I found the mass of one carbon atom and then I'm just going to divide it by 12. So when you divide it by 12, you'll get the one atomic mass unit that will be approximately equal to 1.66 into 10 power minus 24 gram. Okay, so that will be equal to 1.66 into 10 power minus 24 gram. So it should be clear. If it was like kg, then 10 power minus 27. That's what we'll get. So we took one carbon atom and we divide it by 12 and that value was equal to 1.66 into 10 power minus 24 gram. So this is equal to one atomic mass unit or one unified mass, right? So when we learn nuclear chemistry, generally this one atomic mass unit or one unified mass will come into picture, right? So when you have to measure such a microscopic quantity, you will use this unit, which is like atomic mass unit, right? So now let us find what will be the mass of hydrogen atom in terms of unified mass or atomic mass unit, right? So we did the same experiment and we found the answer for hydrogen atom to be equal to 1.67 into 10 power minus 24 gram. Got it? So this was the mass of one hydrogen atom. So if I have to get the mass of this particular atom in terms of unified mass or atomic mass unit, what will I have to do is I'll have to do a simple ratio into it, which is like mass of hydrogen atom was equal to 1.67 into 10 power minus 24 gram, right? I'll have to compare it with unified mass. Therefore, one unified mass will be equal to 1.66 into 10 power minus 24 g, right? If you do the solving, right, 10 power minus 24, 10 power minus 24 will get cancelled out. And then if you do the solving, you'll have to just cross multiply this one. If you do the cross multiplication, you'll get the mass of hydrogen atom in terms of unified mass. So that will approximately be equal to, so mass of one hydrogen atom will be equal to 1.008, okay, unified mass. Got it? So this is approximately equal to 1 U itself, because in hydrogen atom you will just have only one nucleons into it, right? So we'll learn more about that one in classification of elements. As if now this one should be clear. So I took carbon atom and then I divide it by 12 to get the unified mass. So obviously with the case of hydrogen atom, I'll have like only one proton into it. Therefore, it should be approximately equal to 1. Here in this case, it was equal to 1.008 U, right? The difference comes because of the involvement of protons and neutrons. Do not want to worry about that one. The point is, in order to get this unified mass, I used carbon as my standard element. So from that, I got the unified mass. Now I'm ready to compare it with other elements also, right? In the first simple situation, I just took the hydrogen atom. So whatever the case it is, you just have to match it with the mass of the 1 by 12 of the carbon atom. You'll end up getting mass of that particular element in terms of unified mass, right? So this is something that you need to know regarding the atomic mass. So we'll see rest rest concept like average atomic mass, mass percentage, and you have got like some extra stuff into it. So we'll do all those things in the next session. You should be clear with all the concepts that we have discussed in this session. We just saw like 5 different laws. Okay, simple statement based laws. It should be clear. And finally we saw like atomic mass. You should be clear with all the idea that we have discussed, right? With this, the video gets completed. Bye.